This is going to be elastic collision analysis video number 9, and today we're going to be looking at this experiment, this elastic collision experiment by STEM in Action Mandela University. So as we can see, he is using the typical standard POSCO cards. Okay, they have a standard mass of 250 grams. So the red card and the blue card each have a standard mass of plus minus 250 grams. And then on the blue card, we have an additional extra mass, a bar, which also weighs 250 grams. So we should have a 250 grams versus a 500 grams. Now, in the previous video of mine, in my previous number 8 analysis video, Draft Science has made the claim that one of the cards has only 1.5 times the mass as the other card, because the results didn't come out his way. Because again, it was a free momentum experiment. And now, obviously, of course, no, I'm sorry, it's not, it's incorrect. These are standard fabrications, all right? These are standard productions, these POSCO cards, and they always are produced with a mass of plus minus 250 grams. Many people on the internet, many physicists, school teachers use these standard POSCO cards with these with the metal tracks. So for example, in another video, let me see, this one, for example, this is another YouTuber, another YouTube channel using exactly the same cards. And again, and we can see that they give the masses 250 grams for the red mass, for the red card, and 250 grams for the blue card. Now, yeah, they don't weigh them, but why would they lie? Why would every person on the internet lie about the masses? Over here, we have the site of POSCO. Okay. What's that? No, not interested. Come on, get stupid crap. But anyway, we can see here. So we have, these are the exact same POSCO collision cards. And it says right here under the category of features, polycarbonate body, total mass 250 grams. All right, and then we have these additional masses, all right, which are also 250. Oh, come on, fuck off. Oh, there it is. Yeah, so it says these 250 gram masses, all right, they are 250 grams. When we zoom in, we can see it says 250 grams. Now, why would they lie about it? Why would all of them lie about these masses? Now over here, he has a scale, okay? And we do not see him weighing it, but he has a chart where he has written down the weights, the masses. For example, over here, we see the red card has a mass of 244, all right? It is 5 grams short than 250. And then for the blue cards, all right, plus the extra bar on top of it, which should be 500 grams, but it actually is 505 grams, right? So we have a difference of 10 grams extra. Instead of 250 versus 500, we have a 244 versus 505, all right? Which is about 2.06 times the mass instead of a perfect 2. All right, so not that big of a difference. Now let's take a look at the collision.
Facing, so you push it, you'll see it pushes the other car away. So there's a magnet in there, and the other side you'll see there is Velcro strip there, and when they go and they all stick together. So for this part of the experiment, for the elastic collision, you're going to have the magnets facing one another. So on an elastic collision.
Yeah.
Okay, I'm going to set up my experiment like this, and then I'm going to get or Summit to help me, Climate. I'm just going to assist me with this. I'm just going to need to stop the car
almost
before it hits the sensor. Okay, so for this, I'm going to just press record. I'm going to wait 3 seconds, So what I'm going to do now is just going to press record. Wait,
Oh yeah, before I continue, it is important to say that he has motion sensors instead of photo gates, which is a lot more better, okay? Because now we can know the instant velocity after collision. And it's more important, it's more important for the one mass reflecting back. So now we can know the instant velocity, the instant reflection velocity after collision. Because if we have photo gates, all right, the one mass has to travel a certain distance before it enters the photo gate. And the longer that distance is, the longer the time it needs to travel the distance before it enters the photo gate, the more it has to deal with friction and the slower it will get. So it will always measure a slower velocity. But with motion sensors, we can know the instant velocity at the moment it reflects. So that's very nice. So the equation that predicts the velocities after a collision should be more precise in this case.
Seconds and gently push the red card towards the blue card.
There we go. One mass versus two mass. And there we have the graph, the chart.
Okay. From there we have our graph. So now we need to go and determine the initial velocity before the collision and the initial velocity after the collision. Okay, so when we look at our, we're going to take our initial velocity, not somewhere over here, okay, because here we're just waiting for the experiment.
Seems to be seems to be 0.51. I already wrote it down. Let me bring that in over here. Yeah, so the initial velocity is 0.51 meters per second. You can see it over here on the chart. It's 0.5 and it's one block above 1.55 is the initial velocity. And then for the reflection, the card one bounces back with 0.16 meters per second, which is over here. Here is this line is 0.2. We got over here. Well, he says it somewhere in the video.
So both cars are standing still. Yeah, we can know that this
takes so
red graph is going to be for the blue car. Very confusing. We need to keep head about this. Okay.
So hold on. The after collision car 2, the two mass comes out with 0.34 meters per second, which is the red line here, 0.34.
So let's look at the initial velocity. I'm just going to grab my tool.
It takes so long.
My coordinate tool, to add my coordinate tool over here, and I'm going to look at that data point over there. So the first value, that's my x value, that's just time. We're not interested in time at the moment. I'm looking at my velocity.
0.51 initial velocity.
It's going to be 0.51, and our green is the red second. Okay.
Now the two mass after
final
collision.
velocity not going to be over here somewhere. It's just going to be that data point or just after the collision. So my final velocity for my red car is going to be, let's take this point over here.
This is the reflection of part 1.
See that is negative.
Right, so 0.16.
0.1. Just need to convert.
And then we have 0.34 over here. All right, so just to show you that I'm not lying about the velocities. All right, now back to the calculations. All right, here we go. Finally. So again, this is the equation that predicts the velocities after collision. Right, so we had initial velocity of 0.51 meters per second. After the collision, the kart 1 bounced back with 0.16 meters per second. Now, the prediction was, according to this equation, all right, the prediction was 0.17 meters per second. So we have 0.16 versus 0.17. So amazingly close, pretty close, almost perfect. And then, all right, so the measured velocity for car 2 after collision, car 2, the two mass came out with 0.34 meters per second. And the prediction was 0.33. So again, very close, almost perfect. So this equation does a very great job at predicting the velocities. All right, so don't you dare to say that this equation is a piece of crap, and it's nonsense, because this is way too significant, way too significant, all right? Once again, then for momentum, let's calculate the momentums. momentum 1. So the initial momentum before collision is 0.124 kilograms times meters per second. All right. After the collision, car 2 comes out with a momentum of 0.171 kilograms times meters per second. So already here, craft science would say this is a free momentum experiment because it's more than the initial momentum, 124 versus 171. So another free momentum experiment. So something must have gone wrong, or this has been manipulated. This experiment is forced to come out the way of kinetic energy. Once again. All right, so now for the reflection. Cart 1 after collision bounced back with a momentum of 0.039 kilograms times meter per second. All right, so once again, kinetic energy, according to kinetic energy theory, to calculate the conservation of momentum, we have to subtract them because the one mass reflected back in the opposite direction, and therefore has a negative value. So if we do 171 minus 39, we have 132. 0.132 kilograms times meters per second. And the initial momentum was 124. So 0.124 versus 0.132. Pretty close. The difference is 0.008. It's a little bit extra momentum than the initial. So still a tiny little bit of a free momentum experiment, but there's always going to be more or less an error percentage. And in this case, it's a very small error percentage. According to draft science model, we always have to add the momentums together because the momentum and energy are the same. There's no difference. It's a scalar. If we add them together, 171 and 39, we have a total momentum of 210. But the initial momentum was only 124. So we have an increase of 0.086. So a huge free momentum experiment once again. If we are now going to look at the kinetic energies, the initial kinetic energy is, before collision, 0.0317 joules. After collision, car 2 has a kinetic energy value of 0.029 joules, right? And part 1 bounced back with 0.00312 joules. Now we have to add them together, right? The energies of both parts after collision, that adds up to 0.0320, right? And the initial energy before collision was 0.0317. So we have 317 versus 320. So a little tiny bit of extra energy after collision, which should not be possible, but that's probably, it's a very small error percentage. Conclusion, for draft science model, this is once again a free momentum experiment. For kinetic energy, the results before and after collision are almost the same. For momentum, we have 124 versus 132. And for kinetic energy, we have 317 versus 320. These numbers are pretty close together. For draft science, we have 124 versus 210. That's it. Another free momentum experiment. Go ahead and reject this experiment once again. Another experiment to reject, to ignore. Fucking hell.